Welcome! In this session, we'll tackle the problem of converting Roman numerals to integers, a classic problem that tests both your understanding of string manipulation and algorithm design. Let's dive straight into the challenge. In this problem, we are tasked with converting a Roman numeral into an integer. Roman numerals are based on 7 symbols, each of which has a fixed value. These symbols are I, which represents 1, the, which represents 5, x, which stands for 10, l, which is 50, c, which represents 100, d, which is 500, and m, which stands for 1000. To form numbers, these symbols are combined together. For example, the number 2 is written as 2, which is simply 1 plus 1. Similarly, 12 is written as 12, which is 10 plus 1 plus 1. For 27, the representation is xxvii, which is 10 plus 10, plus 5, plus 1, plus 1. Typically, Roman numerals are arranged in descending order from left to right, meaning larger symbols are written first. However, there are exceptions where subtraction is used instead of addition. For instance, the numeral for 4 is not written as I. We'll explore this unique case next. When it comes to exceptions in Roman numerals, subtraction is used in certain cases. For example, the number 4 is written as 4, where the I comes before the v, indicating that 1 is subtracted from 5. Similarly, 9 is written as 9, where I is subtracted from 10. This subtraction rule applies to 6 specific instances. I can precede v to form 4, and I can precede x to form 9. Likewise, x can come before l and c to represent 40 and 90, respectively. Finally, c can precede d and m to form 400 and 900. Given these rules, the problem asks us to take a Roman numeral as input and return its corresponding integer. For example, if the input is 3, the output is 3, since it simply consists of 3 ones added together. To understand this further, let's look at a few examples. In the first example, the input is 3. The numeral consists of 3 ones, which we add together to get the result of 3. In the second example, the input is lvii. Here, we can break it down into its components. L represents 50, V represents 5, and 3 represents 3. Adding these together, we get 50 plus 5 plus 3, which equals 58. Now consider the input mixiv. This example demonstrates the combination of both additive and subtractive rules in Roman numerals. Let's break it down step by step. For the input mixiv, the output is 1994. The breakdown is as follows: m stands for 1000, cm represents 900 because c precedes m, making it subtractive. Next, xc represents 90, since x comes before c, and 4 represents 4, because I is placed before v. When we add these values together, 1000 plus 900 plus 90 plus 4, we get the total of 1994. This example highlights the importance of understanding both the additive and subtractive rules for interpreting Roman numerals. Now let's consider some constraints and edge cases we need to account for in the problem. There are several important constraints and edge cases to be aware of. First, the input string s will have a length between 1 and 15, meaning it can represent any valid Roman numeral between 1 and 3999. The input is guaranteed to be a valid Roman numeral, so we don't need to handle invalid cases. The string will only contain the characters I, V, X, L, C, D, and M. As for edge cases, we need to correctly interpret single symbol inputs such as I, V, or M, which directly correspond to their respective values. Additionally, we must handle subtractive notations like 4, 9, XL, and so on. At the upper limit, the input mum6 represents 3999, while at the lower limit, I represents 1. Ensuring these cases are handled correctly is key to solving the problem. To tackle the problem of converting a Roman numeral to an integer, we first considered a brute force approach. This method involves iterating through the Roman numeral string and using conditional checks to determine the integer value of each symbol. For subtraction cases, like 444 or 949, we add specific logic to handle these scenarios, as they occur whenever a smaller value symbol precedes a larger value symbol. For example, in 4, we subtract 1, the value of I, from 5, the value of V. The steps are straightforward. Iterate over the string, check whether the current symbol represents a subtraction case by comparing its value with the next symbol's value, and either subtract or add the current symbol's value to the total. This approach processes each character once, resulting in a time complexity of O(n), where n is the length of the Roman numeral. While efficient in terms of time, this method relies heavily on conditional checks for each character, which can become verbose and less elegant to implement. To improve on the brute force approach, we can use an optimized method that incorporates a hash map. The hash map allows us to store Roman numeral symbols as keys and their corresponding integer values as key-value pairs, enabling constant-time lookups. This simplifies the implementation and reduces the need for repetitive conditional checks. The process starts by initializing a hash map with all Roman numeral values and a variable to store the total sum. As we iterate through the string, we use the hash map to quickly retrieve the value of the current symbol. If the current symbol's value is less than the value of the next symbol, we apply the subtraction rule, otherwise, we add the value to the total. Once the iteration is complete, we return the total value. This approach maintains the same time complexity of O(n), but is more concise and easier to read, with the hash map requiring only O(1) space. Ultimately, the chosen strategy is the optimized approach using a hash map. The key insight here is recognizing that the primary complexity comes from the subtraction rule, which only applies when a smaller symbol precedes a larger one. This understanding allows us to simplify the logic considerably. By leveraging a hash map, we achieve constant time lookups for each symbol, ensuring that the solution is both efficient and easy to follow. This approach is preferred over the brute force method because it eliminates excessive conditional checks, resulting in cleaner and more maintainable code. While the time complexity remains O(n) for both approaches, the hash map-based solution stands out for its modularity and adaptability, especially if the problem were to expand with additional rules or symbols. In summary, the hash map approach strikes the right balance between clarity, efficiency, and alignment with the problem's constraints, making it the most effective solution for this task. To solve the problem of converting a Roman numeral string into an integer, we need to understand the core representation of Roman numerals. They are built using 7 symbols, I, V, X, L, C, D, and M, which correspond to the integer values 1, 5, 10, 50, 100, 500, and 1000, respectively. Additionally, Roman numerals use a subtraction mechanism for certain combinations, such as 4 for 4 and 9 for 9. The task is to compute the integer equivalent of a given Roman numeral string. The first step in our algorithm is to create a mapping of Roman symbols to their integer values. This can be accomplished with a dictionary in Python, where each Roman numeral is a key, and its associated integer value is the corresponding value. This dictionary allows us to quickly look up the value of any Roman numeral symbol in constant time. Once we have this mapping, we initialize 2 variables, total, which will store the result of the conversion, and prev_value, which helps us keep track of the last processed value. Both are initialized to 0 to set up the computation process. Now that we have our Roman numeral to integer mapping and initialized variables, we can begin processing the input string. To correctly handle the subtraction cases, we iterate through the Roman numeral from right to left. This ensures that smaller values preceding larger values, like in 4 or 9, are handled properly. For each character in the string, we retrieve its integer value from the dictionary. Then, we compare this value to prev_value, which represents the last processed value. If the current value is smaller than prev_value, it indicates a subtraction case. For instance, in the Roman numeral 9, when we process I, its value, 1, is less than the previous value, 10, so we subtract it from total, resulting in 9. On the other hand, if the current value is greater than or equal to prev_value, we simply add it to total. For example, in 6, when processing V, its value, 5, is greater than the previous value, 0, so we add it to total. After each step, we update prev_value to the current value in preparation for the next iteration. Once all characters are processed, the total variable contains the integer equivalent of the Roman numeral, which we then return as the result. This approach works efficiently due to a few key insights. First, iterating from right to left naturally aligns with the subtraction logic of Roman numerals. When a smaller value precedes a larger one, we subtract, otherwise, we add. This simple comparison eliminates the need for complex logic or pre-computations. The subtraction rule, where smaller values before larger ones reduce the total, is seamlessly handled by comparing the current value to the previous one. In terms of efficiency, the algorithm processes each character in the input string exactly once. Since dictionary lookups for the integer values are performed in constant time, the overall time complexity is O(n), where n is the length of the input string. The space complexity is O(1), because the dictionary size is fixed, containing mappings for only the 7 Roman numeral symbols, and no additional data structures are required. To ensure robustness, it's important to handle edge cases. For example, if the input string is empty, we can return 0 or treat it as invalid. For a single character Roman numeral, such as I or V, the algorithm will simply return the value of that symbol. Complex cases like 49449 or MXIV 41994 are handled naturally by the subtraction logic. Additionally, we can validate the input string to ensure it contains only valid Roman numeral characters. Let's walk through an example to see the algorithm in action. Consider the Roman numeral MXIV. First, we initialize total to 0 and prev_value to 0. Starting from the rightmost character, we process v, which has a value of 5. Since 5 is greater than prev_value, 0, we add it to total, giving us a total of 5, and update prev_value to 5. Next, we process I, which has a value of 1. Since 1 is less than prev_value, 5, we subtract it, resulting in a total of 4, and update prev_value to 1. Then, we process C, with a value of 100. As 100 is greater than prev_value, 1, we add it, bringing the total to 104, and set prev_value to 100. Continuing, we process X, valued at 10. Since 10 is less than prev_value, 100, we subtract it, resulting in 94, and update prev_value to 10. For M, with a value of 1000, we add it because it's greater than prev_value, 10, giving a total of 1094, and update prev_value to 1000. Next, we process C, valued at 100. As 100 is less than prev_value, 1000, we subtract it, resulting in 994, and update prev_value to 100. Finally, we process M, with a value of 1000. Adding it gives us the final total of 1994, which is returned as the output. In terms of complexity, the algorithm runs in O(n) time, where n is the length of the input string, and O(1) space. While optimizations like pre-computing subtraction cases can be applied, they add unnecessary complexity and are not needed for this clean, efficient implementation. Here, we define a Python class called solution and implement the method Roman2int, which converts a Roman numeral string into its integer equivalent. To start, we create a dictionary called Roman_map that maps each Roman numeral character to its corresponding integer value, such as I to 1, V to 5, and so on. We then initialize two variables, total, which will store the final result, and prev_value, which helps us keep track of the last processed numeral's value as we iterate. The key part of this implementation is the for loop, where we iterate through the input string in reverse order. This ensures that we can handle the subtraction rule of Roman numerals correctly. For each character, we look up its integer value in the Roman_map dictionary and store it in current_value. At this point, we check whether the current numeral's value is less than the previous one. If it is, we subtract it from the total, as required by the subtraction rule. On the other hand, if the current numeral's value is greater than or equal to the previous one, we simply add it to the total. This ensures that we are accurately summing up the values while respecting the Roman numeral rules. After processing the current numeral, we update prev_value to the current_value so that it's ready for the next iteration. Once the loop completes, the total variable contains the integer representation of the input Roman numeral, and we return it as the final result. This approach ensures an efficient solution with a time complexity of O(n), where n is the length of the input string. Here, we start by importing the necessary utilities and defining our solution class with the method Roman2int, which converts a Roman numeral string into its integer equivalent. To facilitate this conversion, we first create a hash map called RomanMap, where each Roman numeral character maps to its corresponding integer value. This includes I as 1, V as 5, X as 10, and so on, up to M, which represents 1000. Next, we initialize two variables, total, which will store the final result, and prev value, which helps us keep track of the last processed value as we iterate through the string. The string is traversed from right to left, ensuring that we can correctly handle scenarios where smaller values appear before larger ones, such as in 4 or 9. Inside the loop, we retrieve the current character's value from the hash map using romanmap.get s.char at I. At this point, we evaluate whether the current value is smaller than the previous value. If it is, we subtract it from the total, because this indicates a subtraction case in Roman numeral rules. On the other hand, if the current value is greater than or equal to the previous value, we add it to the total, as this represents a standard addition case. After updating the total appropriately, we set prev value to the current value to ensure the comparison works correctly for the next iteration. This logic is repeated for every character in the string until we've processed all of them. Once the loop completes, the total variable contains the final integer representation of the Roman numeral string. Finally, we return this total as the result. This implementation efficiently handles all valid Roman numeral strings by leveraging the hashmap for quick lookups and iterating through the string in reverse to simplify the logic for handling subtraction cases. To begin, we're tasked with converting the Roman numeral 3 into an integer. We start by setting up a mapping of Roman characters to their respective values, called Roman_map. In addition, we initialize two variables, total, which will store our final result, and prev_value, which keeps track of the value of the previous Roman numeral as we iterate through the string. In the first iteration, the character is I, so we look up its value in Roman_map, which is 1. Since the current value, 1, is greater than or equal to the previous value, 0, we add it to total, making the total now 1. We then update prev_value to 1 for the next iteration. In the second iteration, the character is again I, and its value is still 1. As before, since the current value is equal to the previous value, we add it to total, bringing the total to 2. We update prev_value to 1 once more. In the third and final iteration for this example, the character is again I, and its value remains 1. Since the current value is still greater than or equal to the previous value, we add it to total, resulting in a final total of 3. After completing all iterations, we can confidently say that the integer representation of 3 is 3. Now, let's move on to a slightly more complex example, converting 9 into an integer. As before, we start by initializing Roman_map, total, and prev_value. These will help us process the Roman numeral step by step. In the first iteration for 9, the character is x, which has a value of 10 according to Roman_map. Since the current value, 10, is greater than or equal to the previous value, 0, we add it to total, making the total now 10. We then update prev_value to 10. Next, in the second iteration, the character is I, which has a value of 1. This time, the current value is less than the previous value, 10, so instead of adding, we subtract it from total, reducing the total to 9. We update prev_value to 1. After completing these iterations, the final total is 9, which is the integer representation of 9. Now, let's work through an even more complex example, converting maxiv into an integer. We begin with the same setup, Roman_map, total, and prev_value are initialized. In the first iteration, the character is v, which has a value of 5. Since the current value, 5, is greater than or equal to the previous value, 0, we add it to total, making the total 5. We then update prev_value to 5. In the second iteration, the character is I, which has a value of 1. This time, the current value is less than the previous value, 5, so we subtract it from total, bringing the total down to 4. We update prev_value to 1. In the third iteration, the character is c, which has a value of 100. Since 100 is greater than or equal to the previous value, 1, we add it to total, making the total 104. We update prev_value to 100. In the fourth iteration, the character is x, with a value of 10. Here, the current value is less than the previous value, 100, so we subtract it from total, reducing the total to 94. We update prev_value to 10. In the fifth iteration, the character is m, which has a value of 1000. Since 1000 is greater than or equal to the previous value, 10, we add it to total, bringing the total to 1094. We then update prev_value to 1000. In the sixth iteration, the character is C, which has a value of 100. Since the current value, 100, is less than the previous value, 1000, we subtract it from total, reducing the total to 994. We update prev_value to 100. Finally, in the seventh iteration, the character is M, which has a value of 1000. Here, the current value is greater than or equal to the previous value, 100, so we add it to total, resulting in a final total of 1994. With all iterations complete, we determine that the integer representation of maxiv is 1994. In this problem, the time complexity of the Roman toInt method is O(n), where n refers to the length of the input string s. This is because the algorithm processes the string in a single pass, iterating through each character exactly once. During this iteration, each Roman numeral character is converted to its integer value using a predefined dictionary, which allows for O(1) average time lookups. Since there is one dictionary lookup for each character, this step contributes a total of O(n) operations. Additionally, for each character, the algorithm performs a constant number of basic arithmetic operations such as addition, subtraction, and comparisons. These operations are O(1) per character, which adds up to O(n) for the entire string. When we combine the time contributions of the iteration, dictionary lookups, and arithmetic operations, the total time complexity is O(n). The space complexity of the Roman toInt method is O(1), meaning the memory usage remains constant regardless of the size of the input string. First, the Roman_map dictionary, which contains mappings for the 7 Roman numeral characters, is predefined and occupies a fixed amount of memory that does not scale with the input size. Next, the algorithm uses a few variables such as total, prev_value, char, and current_value to track intermediate results during execution. These variables also require a constant amount of memory. Lastly, the input string s is not modified or duplicated during the process, ensuring no additional memory is allocated. Since no other data structures or memory allocations are made, the overall space complexity is O(1). To highlight the efficiency of this approach, let's compare it to a naive solution. In a brute force method, you might iterate through the string and use multiple conditional checks, like if char == I, to determine the value of each Roman numeral. While this naive method would still achieve O(n) time complexity due to the single iteration over the string, it would be less efficient because repeated conditional checks are slower than the O(1) dictionary lookups in the current approach. The space complexity for both methods remains O(1), as neither approach requires additional memory that scales with the input size. Moreover, whether we analyze the best, average, or worst-case scenarios, the current approach consistently achieves O(n) time complexity, as every character in the string is processed exactly once. Similarly, the space complexity remains O(1) across all cases. From a mathematical perspective, the big O complexity of this algorithm is straightforward to justify. The algorithm performs a single pass over the input string, which contributes O(n) operations, where n is the length of the string. For each character, a dictionary lookup is performed in O(1) time, and a constant number of arithmetic operations are executed. These steps combine to give an overall time complexity of O(n), as the number of operations scales linearly with the string length. On the space complexity side, the memory usage remains constant at O(1), because the predefined dictionary and a small set of variables occupy fixed memory, independent of the input size. No additional data structures are created that scale with the input, reinforcing the O(1) space complexity conclusion. When working with Roman numerals, there are a few common mistakes to watch out for. One of the most frequent errors involves incorrect handling of subtractive notation. For example, the numeral 4 represents 4, but if you mistakenly interpret it as 6 by adding 1 and 5 instead of subtracting 1 from 5, the result will be wrong. To address this, you should check if a smaller numeral precedes a larger one and subtract their values instead of adding them. A simple condition like if value, si plus 1, can help you handle this properly. Another issue is not accounting for the end of the string. If you try to access si plus 1 when I is at the last index, you'll encounter an index out of range error. To avoid this, ensure you include bounce checking or stop iterating at the second to last index and handle the final character separately. Lastly, skipping edge cases is a critical mistake. For instance, you might overlook testing with the smallest numeral, I, or the largest valid numeral, 6, which represents 3999. Always validate your solution with edge cases and consider invalid inputs if the problem specifies them as part of the constraints. Inefficient string operations can also lead to problems when converting Roman numerals. A common example is using string concatenation inside a loop, which can result in n squared complexity. Instead, you should optimize your solution by leveraging pre-computed mappings or dictionaries for direct lookups, avoiding repetitive operations. Another pitfall is misunderstanding the rules of Roman numerals. For instance, allowing invalid numerals like III or VV violates the standard conventions. To ensure correctness, you need to follow the established rules, such as no more than 3 consecutive identical numerals and only valid subtractive pairs, like 4 or 9, should be allowed. By adhering to these principles, you can avoid introducing logical errors into your solution. Understanding the patterns in Roman numerals is key to solving this problem efficiently. The additive and subtractive patterns repeat consistently, so recognizing them can help you design concise, accurate logic. It's also important to be mindful of edge cases, as interviewers often test for scenarios like empty strings, single characters, or the largest valid input. Be proactive about clarifying constraints during an interview to avoid surprises. While iterative solutions are the most common approach, discussing recursive alternatives can showcase your algorithmic versatility and problem-solving skills. Additionally, consider the trade-offs between space and time complexity. For this problem, an ideal solution would be a single-pass algorithm with n time complexity and 1 space usage. For further practice, you can explore related problems such as LeetCode 13, which is the direct Roman to integer conversion, LeetCode 12, which reverses the process by converting integers to Roman numerals, or even LeetCode 171 and 273, which involve mapping numbers to specialized string formats. There are also alternative approaches you can use to tackle this problem. One option is the two-pointer technique, where you compare adjacent characters to identify subtractive notation. While this approach can add clarity to how pairs are checked, it may increase the complexity of your implementation. Another method involves using a hash map for numeral lookups combined with backtracking. This allows you to process each character recursively, though recursive solutions can introduce additional overhead compared to iterative methods. Lastly, you might consider pre-processing the string with regular expressions to identify subtractive pairs like 4 or 9 upfront. This can simplify downstream processing but comes with its own trade-offs, as regex patterns could add unnecessary complexity and may not be as efficient as direct iteration. Each of these approaches has its strengths and weaknesses, so understanding their trade-offs will help you choose the best fit for your specific needs or constraints. Great job! We've successfully solved the Roman numeral to integer conversion problem. Remember, efficient use of hash maps and careful string traversal are key to solving these types of problems. Keep practicing, and don't forget to like and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!